We are pleased to host Dr. Vladimir Petrov, Associate Professor of, at the Radiochemistry Division of Chemistry Department of Lomozhenov Moscow State University. Professor Petrov took his degree in chemistry with honor in 2007 with a thesis work concerning research of solubility of uranium oxide samples and desorption behavior towards Neptunium-5 at Chemistry Department of Moscow State University, and his PhD degree in 2011 with a thesis concerning the solubility and sorption behavior of Neptunium-5 in high salt solutions. Since 2002, he works in laboratory of thermochemistry in physical chemistry division, and since 2005 is involved in the laboratory of dosimetry and environmental radiochemistry and at Moscow State University. He spent a period of more 1 year at Karlsruhe Institute of Technology in the group of Dr. Markus Altmaier, improving scientific results in solubility and phase transformation of Neptunium-5. In 2010, he is involved as enrolled as engineer at Chemistry Department of Moscow State University. In 2012, researcher at Moscow State University, and since 2013 till now is associate professor and head of the lab of dosimetry and environmental radioactivity in Moscow State University. Is author and co-author of more than 50 papers on international journals. So the floor is yours, and thank you for coming and thank you for your webinar.
Thank you, Professor Mariani, for this introduction. And I will start sharing my screen. And today's lecture, thank you for inviting me for this webinar. And we will talk a bit about the basics of nuclear fuel cycle and generation of radioactive waste during the way of uranium from mining to disposal of nuclear waste. And the important part of this lecture for, let's say, for public, that when we talk about the nuclear energy, we usually imagine that there is a nuclear power plant or nuclear reactor, and the whole story is in that facility. But it's not true, and we will see today what is the long way of uranium or nuclear fuel from the very beginning to the very end. And what is the current situation with energy today? It's honestly not such a good situation. Living in Russia or in Europe, maybe we can not see this, but actually there are around 1 billion of people living with energy poverty, and the situation has to be improved, and we need more and more sources of energy, and one of the way to produce energy is of course to use nuclear energy. Why it is so? Because also it was a statement from previous IAEA, International Atomic Energy Agency director, that by 2050, if climate change goals are to be met, around 80% of electricity will need to be low carbon. So nowadays, around 70% of electricity comes from fossil fuels like coal, oil, gas, and we need to decrease this 70% to 20% in less than 30 years. And low carbon means that we need to use wind energy or solar energy or hydropower energy or nuclear energy. And if we will compare um sources of energy by their risks and greenhouse gas emissions, we will see that these four sources of energy, and this renewable energy like wind, solar, hydropower, and nuclear energy, they produces much lower, much less greenhouse gases, CO2 means. And also, if we will compare the risks for human, for people who are working in these areas, we will see that number of deaths, means, let's say risks for people who are working there, is much lower for these four sources of energy. And for nuclear energy, it can be very surprising as far as we um, hear very often accidents like Fukushima and Chernobyl, that these disasters resulted in many deaths, but it's not true. And if we will look in statistics, we will see that the actual death rate coming from nuclear energy is very low, and it's comparable with solar, wind, and hydropower. But if we will see these death rates from, let's say, traditional sources of energy like coal, oil, and natural gas, we will see that there are very huge death rate. According, it's mainly come from mining, and also it's it's over death rates due to air pollution in the houses. So again, these four sources of energy, including nuclear energy, are the safest and the cleanest sources of energy. Also, if we compare how much of fuel we need to produce the same amount of energy, we will see that the volume of the nuclear fuel that is required for the production of the same amount of energy is a million times lower, smaller than the volume of the traditional fuel like gas and coal. Also, if we compare nuclear energy to wind energy or solar energy, we will see that the area that is required for the nuclear power plant is, um, let's say, 100 times less than the area that is required for the wind turbines and solar panels. So, all these four, let's say, the safest and cleanest sources of energy uh, combined, let's say, in so-called green square. That means that a combination of wind, solar, hydropower, and nuclear energy. And nuclear energy now has a potential very important role in securing electricity supplies and, as uh, long-term supplies and short-term requirements for the current needs, etc. And the important role of scientists and people who are speaking with the stakeholders, with public, is to build the trust of the public. And the important way to do this is to demonstrate how we can safely handle all the nuclear waste, and how we can safely perform the decommissioning of existing nuclear facilities and the facilities that will be built in the future. So, to begin, we will start with this lecture on nuclear fuel cycle. And nuclear fuel cycle is not only a nuclear power plant or nuclear reactor that produce electricity and heat. Nuclear fuel cycle includes all the operations from the uranium or mining to production or fabrication of nuclear fuel, and then then disposal of spent nuclear fuel, or disposal of radioactive waste that arise from the reprocessing of the spent nuclear fuel. And if we reprocess spent nuclear fuel, that means that we extract valuable components, we divide all the radioactive waste by their properties. But the most important part is extraction of valuable components that we can use again to fabricate the fuel. Then it is called the closed nuclear fuel cycle. So we made it like really a cycle. And if we directly dispose the spent nuclear fuel without any reprocessing, without any treatment, then it is open nuclear fuel cycle. And nuclear fuel cycles, again, in the beginning, it has the main steps like uranium extraction from ores, then it is uranium enrichment, and then conversion of uranium hexafluoride to uranium dioxide mainly to fabricate nuclear fuel. But what is the radioactive waste? So first of all, as far as it is radioactive, that means that it is the material that contains or is contaminated with radionuclides. Okay, and as far as it is waste, that means that this materials is has no use in current situation with current technologies. But it's not the complete term, because if we will look on many materials that even our human body contains natural radionuclides like carbon 14 or potassium 40 or tritium or other many natural radionuclides. That doesn't mean that our body is radioactive waste. Material that contains radionuclides at concentrations greater than clearance levels, and which have no use with current technologies, that materials are radioactive waste. And clearance levels are the levels that say you that this material is radioactive waste, and this material is no longer considered as radioactive material. And these levels, there are recommendations by International Atomic Energy Agency, but the most important part of these levels that they're established by countries, by regulatory bodies in individual countries. So all the international organizations, they can say only, they can give you only recommendations, but all the levels they established by countries, by government of the countries. And interesting part, or very um, benefit, if we can say it, of the radioactive waste, that they're decaying. So there is a law of radioactive decay that says us that with time, the number of radionuclides is decreasing. That means that the radionuclides decay to another radionuclide and to another radionuclide until the decay chain reaches the stable nuclide. That means that the relative hazard that is arised from radioactive waste is finite. There is a graph of relative hazard index of different compounds, and SNF is spent nuclear fuel, so it's the most dangerous, hazardous material in the world, the fresh spent nuclear fuel. And but with time, you see there is a log scale, time scale. So it is 10 years, 100 years, 1,000 years, and finishing with million years. With time, the hazard of spent nuclear fuel is decreasing because of decay of radionuclides inside the spent nuclear fuel. And this is not the case for, let's say, heavy metals like mercury or chromium or other heavy metals that have that do not decay. So that means that the hazard will be forever with us. So it's if we can say a benefit of the radioactive waste that they're decaying. And where all the radioactive waste are coming during the nuclear fuel cycle, the right answer is that at every step, at every stage of nuclear fuel cycle, we generate nuclear waste or radioactive waste. And we will start with the mining of uranium ore. There are at least three types of mining. It's open pits like careers, or it's mining, or it's underground leaching. The choose or the choice of the type of mining depends on the current situation or on the geological situation of the in the area of uranium ore location, and of course the most safest, the most green, let's say, way is the underground leaching, because during the underground leaching there is no excavation of the earth, of the soil. It's only drilling of the wells, of injection wells and recovery wells, and there is no impact on the surface of the territory. So it's very ecological way to mine the uranium ore, but unfortunately, the s- some specific conditions should be in this area to perform this type of mining, this underground leaching. For open pits and mines, the main way to extract uranium is the leaching of uranium from the heaps. So all this ore, they are located in the form of heaps, and the acid, mainly it's sulfuric acid, is uh, dripping on the top of this heap, and it's leaches the uranium from the ore, and all this liquor is collected and then transferred to the plant. The uranium is extracted and purified, and as far as we have all these heaps, we produced a lot of tailings during the uranium mining, and these tailings they contain so-called norm waste. It is naturally occurring radioactive matter. It is all the products of the uranium decay, radium, radon, polonium, thorium, and their decay products as well. And of course, these tailings, they have linings under them, but this lining with time is degraded, and due to the rains, due to the natural groundwaters, all this norm waste, all the components of this norm waste coming with natural waters to rivers, to the whole surrounding territories. So this is the first, let's say, first uh, radioactive waste containing only natural radionuclides, but still these natural radionuclides, their concentration in tailings are above this clearance level, so they're uh, considered as radioactive waste. And then the uranium that is extracted and purified, converted to a specific chemical form. Uranium hexafluoride. This is the last compound here. And you can see how many steps uranium is going through. And at each of these steps, we produce also radioactive waste containing uranium decay products and other components. And why do we need uranium hexafluoride? Because it has very nice properties. It can be converted to gas without going through the liquid stage. That means sublimation. And the temperature of this process is quite low, just 56 Celsius degrees. And yeah, it's waste what we also generate. And we can use this gas, this uranium hexafluoride, to enrich uranium. Why do we need this enrichment? In most of the nuclear reactors, the uranium-235 is the main radionuclide that is fissile under the action of thermal neutrons, and that means the slow neutrons. And these reactors they requires the enriched uranium, so that means the high concentration of uranium-235 than in natural uranium. In natural uranium, there is only 0.72% of this isotope, uranium isotope, and we need at least 2 to 5% of the uranium-235 in our fuel so nuclear reactors will work. And as far as we enrich one part of uranium, we deplete another part of uranium. And in all these processes, we produce two streams of uranium: enriched uranium and depleted uranium. So again, this uranium hexafluoride is in gaseous form at elevated temperature, and due to a small difference in mass, uranium-235 and uranium-238, they have a little bit different velocity and a little bit different rate of diffusion through the membrane. And we can use this very small difference in the velocities to enrich uranium. So the uranium-235 hexafluoride will move a little bit faster than uranium-238. And if we repeat the process of this separation many times, then we can produce um, enriched uranium. But again, as far as there are two streams of uranium, let's say one is useful enriched uranium and one is the depleted uranium. So we generate quite a lot of waste in the form of uh, toxic, chemically toxic uranium hexafluoride. The activity of uranium, of depleted uranium, is lower than natural uranium, and so the main hazard of this depleted uranium hexafluoride is the chemical toxicity of this compound, and usually it's stored in such containers or barrels produced from stainless steel, and it's stored on the uh, surface, daylight surface, and you can see the question sign at the end of the title: is it waste or not? As we remember from the term of radioactive waste, it's a material that is currently has no use. But depleted uranium can be used, for example, in fast neutron reactors. And currently, there are fast neutron reactors in operation in Russia. So we can consider these depleted uranium hexafluoride not as a waste, but as a source of uranium for future technologies. And from my point of view, we cannot call it a waste, because with the development of reactor technologies, we can use this depleted uranium as a fuel. So we will be able to use it again. And after enrichment, we then fabricate nuclear fuel. Nowadays, the most popular, most used nuclear fuel is in form of uranium dioxide or mixed oxide of uranium and plutonium, that is called MOX fuel. So it's mixed oxide MOX fuel. There are plenty of other types of fuels used for research reactors or for transport reactors or for other purposes, but yeah, the most popular form is uranium dioxide in the form of these tablets. And these tablets, they're very small. It's around 8 millimeters in diameter and 2.5 centimeter in length, depending, of course, on design of the assembly of these nuclear fuels. So all these tablets, they are located in the fuel rods, and these fuel rods, they assembled in fuel assembly, and this shape of fuel assembly can be different depending on the design of the reactor. And during the fabrication, the fuel can be produced with some defects, or at the production plant, there can be old fuel that is stored for several years, and all this fuel with defects, or this stored old fuel, they have to be purified and refabricated, and to do this, they are dissolved, and that means that during the purification and refabrication, we produce again liquid radioactive waste of complex composition with salts, with acids, etc., that have to be treated for further disposal. And now nuclear fuel is assembled and in fuel assembly, and we put it in nuclear reactor at nuclear power plant. There are different types of nuclear reactors, so we will not go through them. But the main scheme of nuclear power plant is more or less the same for all the designs. It contains a reactor itself. The fuel is produced a lot of heat. This heat is transferred to heat carrier that is going in this cycle, and heat carrier transfer the heat to water, mainly to water, that then transform to steam, and then steam rotate turbine, and turbine connected to generator, and generator produce electricity. Steam then condensate in water, and then water again heated by heat carrier again goes to steam, etc., etc. It's a cycle again. So it's the main design of any nuclear power plant, and even if we have no release of radionuclide outside of the nuclear power plant, we have nuclear waste in nuclear power plant, because the water that is used in nuclear power plant is needed to be very pure, and to purify this water, uh, people use this ion exchange resins. So it's organic compounds or organic materials that absorb all the ions in water. It works. The scheme of these filters is the same as you can use at your home to purify the tap water. So it's more or less the same resins. And all these resins, as far as they absorb radionuclides from the water, they become radioactive waste, and they are stored currently at nuclear power plants. Yeah. During the heat production, nuclear fuel is decaying, so uranium is divided onto two parts, producing a lot of energy, and uranium then transformed to another elements. So during the work or production of heat, the nuclear fuel changes its composition. So there are plenty of new chemical elements now present in nuclear fuel that change dramatically its structure, its thermal conductivity, volume, mechanical strengths, and other characteristics like neutron capture, cross section, and etc. So with accumulation of this new for nuclear fuel chemical elements, the fuel becoming not useful for further applications. So it's becoming more and more hard, more and more difficult to use this fuel to produce heat with in safe mode, let's say. So with time, nuclear fuel is changed with fresh nuclear fuel, and the spent nuclear fuel then has two different phases. Either we reprocess it or not. Why we can reprocess spent nuclear fuel? Because actually in spent nuclear fuel there are plenty of useful reusable material. There are almost all uranium is there still. There are only 3% of fission products that cannot be used further, and 97% is a reusable material that we can extract and use it again for fabrication of fresh nuclear fuel cycle. So from this point of view, we can say that spent nuclear fuel is not always radioactive waste. It depends on the strategy of the country. Either the country uses open nuclear fuel cycle, where spent nuclear fuel directly disposed without any reprocessing, or country uses so-called closed nuclear fuel cycle, where we extract or separate the valuable reusable components of spent nuclear fuel. Um, but it's not the only benefit of reprocessing of spent nuclear fuel. Another benefit that we can decrease the long-term hazard of this material. There's a graph where you can see the again relative radiotoxicity of the spent nuclear fuel. It's the red line is the total radiotoxicity, and this pale green line is the radiotoxicity of natural uranium ore. And you can see that only after, let's say, 200,000 years, the spent nuclear fuel will have the same radiotoxicity as natural uranium ore. So that means that we put in the environment the same amount of activity as we took from the environment, and it requires 200,000 years without reprocessing. But if we extract all the long-lived radionuclides, mainly it's actinides like plutonium and americium, Uh, then we will see that this radiotoxicity will reach the level of natural uranium ore in only 300 years. And it's a, time scale that we can easily see in the human history. It's not such a long story in this 300 years. Uh, Especially in comparison with hundred of years, 100,000 of years. So uh, if we extract actinides, that doesn't mean that they will disappear. But again, with the modern technologies of the fast neutron reactors, we can transmute all these long-lived radionuclides. That means that we transform them into shorter-lived radionuclides with half-lives of 10, 20 years or less. And we also can transmute not only actinides, but also such long-lived radionuclides as technetium-99 and iodine-129. And to do this, we can either use the existing uh, fast neutron reactors in Russia. They called BN reactors with the heat carrier sodium in there, or there is a new reactor that is developed in Russia again that is called BREST, and that means that it is the fast reactor with natural safety. And in this reactor, the heat carrier will be lead. So we can decrease the long-term radiotoxicity of components of spent nuclear fuel, and also we can decrease the waste volume by reprocessing of spent nuclear fuel cycle. So there is a nice photo. I took it from one of the in one of the conferences, but I don't remember the offer of this photo. So sorry for that. And there is a nice representation of the volume of high-level waste generated by nuclear energy for the one family in entire lifetime of this family. And if we extract actinides and transmute them, then the volume will be even less, like this diamond in the ring of the lady. But how to reprocess, how to separate radionuclides from spent nuclear fuel? And the main technology currently used is a liquid extraction. And one of the main process that use liquid extraction called Purex process, that is plutonium uranium redox extraction. So there is a scheme. I will not go in detail, but the main idea that uranium and plutonium, so it's fissile components of spent nuclear fuel, they are extracted and separated from all the fission products. And then using the reducing agents, plutonium is reduced to plutonium-free and back extract from the organic phase, and uranium remains in the organic phase. And so far we can separate uranium and plutonium to produce different types of fresh nuclear fuel. And but during this step of extraction of uranium and plutonium, we produce so-called raffinate or high-level waste. And from this high-level waste, we can again reprocess it and extract all the long-lived actinides. And to do this, there are plenty of new processes that are developed in different countries, and there are many names. It's not the whole list of different processes. So there are plenty of new technologies that are development to reprocess radioactive waste and to let's say to do them more safe. Um, yeah, but during the reprocessing, again, we produce quite a huge amounts of liquid waste. And in at very beginning of nuclear age, this liquid waste they either uh, put it into natural or artificial lakes and even rivers, or they are stored in such a huge tanks again near the rivers, and all this liquid waste they have to be reprocessed, immobilized and disposed. And when we talk about the disposal, that means that we uh, use so-called multi-barrier concept. So we first transform all the waste in the um, very safe form. We immobilize all the radionuclides. For high-level waste, we use vitrification, so we transform all the radionuclides in glass form. For other types of radioactive waste, we can use cementing or uh, or other technologies. So, but anyway, we immobilize all the radionuclides in a very compact and stable form. Then we pack this form in canister, let's say, and then we put this canister in host rock in the special repository, and we fill the space between the uh, canister and the host rock with special buffers. So it is very complex engineering task. There are specific requirements for every material that we use for this. Barriers, and it is like this Russian doll called Matryoshka, where in the center we put our immobilized waste form, and then we protect with this waste form with multiple barriers. And the nuclear fuel cycle is not the only source of radioactive waste, because we use radioactive substances in many fields of application, starting from industry for tomography. We use it in medicine, in research, of course, and also in food and agriculture applications. And we, even if we produce non-radioactive metals like rare earth metals, for example, we produce so-called norm waste, that is natural radionuclides concentrated in the B products, etc. So at the end, I would like to make some very brief conclusions that nuclear energy is the main component of nuclear energy, of course, a nuclear power plant, but it's not the only component of the whole nuclear fuel cycle, because it's all the steps from uranium mining to the disposal either of spent nuclear fuel or radioactive waste. And the radioactive waste is the result of any activity when we use radioactive substances or radionuclides. And spent nuclear fuel itself is not always the radioactive waste, because we can use the reusable materials from extracted from this. And fractionation and transmutation of radioactive waste can significantly reduce the activity, the long-term hazard of these materials. And the main method currently used for spent nuclear fuel reprocessing is Purex process, and the im- main and important part in radioactive waste storage and disposal is a multi-barrier concept or system. And the last but not the least, that it is important to remember that the hazard from radioactive waste is finite. So thank you for your attention. If you if we will have any questions, I will try to answer them.
Thank you, Professor Petrov, for your talk, very clear. If there are some questions, comments, please. If not, we can start with a small question, but probably that require a very, very big answer. But don't worry, just to give an overview, not so detailed, concerning the partitioning, the fractionation of spent nuclear fuel. What is the state of art in Russia? For example, are you looking more in the direction of hydrometallurgical processes or pyro or both? And a general overview about the state of art.
Yeah, so there are two main concepts for partitioning. Of course, for old fuel or spent nuclear fuel that is stored for, I don't know, 30, 50 years, we can use only hydrometallurgy because it is already not so hot, not so active, and all the aqueous solutions, of course, there will be some radiolytic process, but they will be not so intensive. And so far, we can use this aqueous solution, organic solutions, and we have project, a big national project, to separate these long-lived actinides like americium and neptunium for further transmutation. Uh, and there is a second way is to deal with the fresh spent nuclear fuel with the short storage time, like 2-3 years. It is still very hot and active material, and we cannot use solutions, aqueous solutions. And for this, we are looking for pyrochemistry. And there is it will be a first how to say it demonstration, but in the scale of a plant. Um, it will be constructed in Siberia, near the Tomsk city. It will be this new reactor, Brest, fast neutron reactor, and all the stages of fuel fabrication, fuel reprocessing, all these technologies will be located in one place. So it will be like a closed nuclear fuel cycle in the area of one plant. And for this, yeah, it will be a combination of pyrochemistry and hydrometallurgy. So for the first separation of all the fission products that are really active, they have very high relative activity. They all will be separated from uranium, plutonium, americium, neptunium by pyrochemistry, and then all these further reprocessing steps will be done with hydrometallurgy. So it's like a combination of two
Yes.
technologies.
And so you have pilot plant in operation, little pilot plants for studying hydrometallurgical partitioning and
Yeah,
pyros.
for hydrometallurgical partitioning, we have several facilities in Russia. It's a very long history of research in Ozersk. It's in Ural Mountains, in Krasnoyarsk. It's in Siberia. So yeah.
And not only for the Purex
Yes,
also
yes. Also
for the advanced
yes,
partitioning processes.
for new processes as well. Yeah, we it's again like several not so big projects, but still quite big for for us as scientists. So it's
Yes.
a collaboration with universities, with institutes, and with these facilities where we can work with such active materials. Because at the universities or even in institutes, very often we cannot handle with these spent nuclear fuel materials, etc. So it's a collaboration always, and we can yeah, use their facilities to check if our ideas are correct. And for pyrochemistry, um, as far as I know, there is only, um, let's say, a lab scale research. And currently, again, for this pilot plant, there is a big project to produce all these cameras, inert cameras.
Yes.
It's a very big problem because they have to be very big and inert without any even small holes, etc. So it's very complex technological task to produce even equipment, not just to perform research studies, but just to make all the equipment. It's requires a lot of efforts, and they are working on it now. Yeah.
Thank you. As you know, we are involved in Polimi with in studying some partitioning processes of course, within the European Commission support. And some colleagues from Russia will participate in some meeting. And I hope we can collaborate with Russia because it's an important goal for the sustainable development of fission nuclear reactors,
Yeah,
of course.
that's true. I think that all these areas of research, the main goal of all these research studies is to make all this nuclear energy production safe, more safe. Um, and nowadays, the problem of radioactive waste is a very urgent uh, task because we accumulated a huge amount of radioactive waste, and we need more new specialists that will bring new ideas. And
We need to solve the problem, of
yeah.
course, quickly. Thank you. Some other questions for Professor Petrov, also from a didactical point of view. I can see a lot of our students or some colleagues from abroad. If not,
Anyway, yeah, if there will
yes,
be
if
any
not,
questions.
I have another curiosity.
Mhm,
But seeing the wide repository of depleted uranium,
mhm.
are there in Russia some studies concerning possibilities of for using this kind of material, not only in
Mhm,
nuclear,
mhm,
because the radioactivity, as you said, is not so high, is lower than natural uranium. And we know, for example, from concerning previous scenarios in wars that the depleted uranium can be used as projectiles
mhm.
for other purposes, but also the metallic uranium is very, very dense with high density material, and so some other possible uses can be considered in the future.
Yeah, there are two main possible application of this uranium. First, still it's for nuclear fuel cycle, but not for fast neutron reactors, because with this technology of the gas centrifuges still developing, and the new generation of this gas centrifuge, they have higher efficiency to enrich uranium. So this old depleted uranium is still can be a source for this new gas centrifuge. So we can enrich again this or deplete again
Yes,
this
yes.
uranium. It is one way to use this depleted uranium, to deplete it and get enriched uranium again. And another use is to use it as a shielding material. Yeah, as far as it's very low active material, and it is more dense than lead. It can be used as a shielding materials in for different facilities, for, I don't know, like
Yes,
in accelerators or whatever.
yes, of course. I think the same.
Yeah, for military purposes, I didn't see in Russia the application of this uranium as a like to put it in the middle of the bullet or whatever it's called. I didn't see these technologies in Russia. Maybe I just don't know about them. So,
Thanks. If you can see the chat, there is a question
mhm.
by Andrea Camerini.
One moment.
If
What
not,
is the amount of
okay,
recycled fuel currently used in Russian nuclear fleet? I think something about 10% of France nuclear electricity comes from MOX fuel. Are there any estimations for Russia? Uh, I don't have numbers by heart. I don't remember them, but yes. So we use MOX fuel for production electricity, but I don't think that is also a big percent at the moment. So it's still a very low percent, maybe also 10 or even less. So.
okay.
Mhm.
Thank you. So we have foreseen a period of 1 hour for this seminar, and uh, this is the end. If no more, there are probably another question or not. No? Thank you. Just thank you. Okay. And thank you again for your speech. Very interesting and very effective. And
Thank you.
also for giving us an overview of the studies in Russia, because we are, of course, very interested in the future cooperation. Thank you very much.
Thank you very much.